Hello everyone. In this video, we will discuss about the various types of elastic constants. Before that one, we will revise the basic concepts of the stress and strain. In the previous lecture, we defined the stress is the resistance offered by the body against the deformation. So observe in the diagram, here we are applying the force, that is the capital P, on a body. Then internally it will be generate the resistance forces. Then the stress sigma is defined as the internal resistance force divided by the cross sectional area, that is sigma equal to P by A. And strain is the effect of the deforming forces, is nothing but deformation per unit length. So strain, that is a epsilon equal to deformation is nothing but change in dimensions. It may be change in length divided by the original length. Then what is the relationship between the stress and the strain? So we know that when we are increasing the forces, it will be increase in the deformation. Is nothing but when we are increasing the applied forces, obviously its dimensions it will be increased. So stress having the direct relation with the strain is nothing but stress is directly proportional to the strain. Same thing is proposed by the Hooke's. So Hooke's law is defining the relationship between the stress and strain, that is ratio of intensity of stress to the corresponding strain is constant within the elastic limit. Same thing we have to observe in the graph, that is, let's see here. So this is the sigma and this is the epsilon. So Hooke's law is stated at so change in the stress and the change in the strain is constant within the elastic limit. Let us consider, so O2A is the elastic limit of the body. So within the elastic limit, here you have to observe that the ratio of the intensity of stress to the corresponding change in the strain, it should be the constant. It's nothing but sigma divided by epsilon equal to constant within the elastic limit. So this constant we are calling as the elastic constant. So this elastic constant is depend upon the type of strain. For the different type of the strains, we are defining the different types of the elastic constants. So here question will be raised. So why elastic constants are depend upon the strains only, not for the stresses? So let's see. Here we have to consider the same dimensions of the steel and aluminium bar and also applying the same amount of the load. Now stresses is generating in the two bodies, it is having the same amount. So here we are applying the load P on the two types of the bars, that is the one is made by the steel, another one is made by the aluminium. Then the stresses generated in the two bodies, it will be same. Why mean? So stress is not depend upon the material properties. It is always depend upon the how much load we are applying and what is the cross-sectional area. So here stress in the two bodies is the load divided by the cross-sectional area. So it is not depend upon the material property, but amount of the strain or amount of the deformation, it will be different for the two different bodies. Why mean? Strain is always depend upon the material properties. So here different types of the elastic constants we are defining, that is the depend upon the different types of the strains. So we have the various types of elastic constants, that is modulus of elasticity capital E, Poisson's ratio mu or 1 by m, modulus of rigidity capital G or N, and bulk modulus capital K. All are depend on the type of strain produced. So first we have to discuss about the type of strains. First one is the longitudinal strain. For the longitudinal strain, type of elastic constant is the modulus of elasticity or Young's modulus. So first we have to see the what you mean by longitudinal strain. So longitudinal strain is defined as the any direct stress produces a strain in its own direction, which means, for example, we are applying the direct stress sigma. Similarly, strain will be produced in the same direction of the stress. So this type of strain we are calling as the longitudinal strain. So in the diagram we have to observe that one. Here we are applying the axial stress, that is the sigma. Nature of this axial stress is the tensile, and applied along the longitudinal axis. So here we are applying the axial stress in the longitudinal axis. Let us consider in the length direction. So now the length of the bar is increased. Then this change in length, that is we are calling as a deformation. This change in length per unit length of the bar is called as a longitudinal strain, or maybe the primary strain. So longitudinal strain is when you are applying the stress in the same direction. So dimensions it will be changed, that is we are calling as the strain. In the same direction of the stress producing the strain we are calling as the longitudinal strain. So in the diagram we are applying the stresses in the length direction. So here longitudinal strain is defined as the change in length divided by the original length. So ratio of the strain to the strain within the elastic limit, it is the constant. That constant we are calling as the modulus of elasticity. So modulus of elasticity is constant of proportionality, which is defined as the intensity of stress that causes for the unit strain. So next we have to discuss about the lateral strain. For the lateral strain, producing the elastic constant is the Poisson ratio. See in the diagram, when we are see here, let us consider this is the P. See in the diagram we have to observe that one thing. When you are applying the forces in the length direction, so in the longitudinal axis, so here we are applying the axial force, let us consider tensile, then the length of the bar will be increased. That is previously we discussed. Respective strain we are calling as the longitudinal strain. But same thing we have to observe in another direction, that is the lateral direction, that is the width point of view or maybe the thickness point of view. So in the width and thickness point of view, these dimensions, this width as well as this thickness, it will be decreased. These corresponding strains we are calling as the lateral strain. So longitudinal strain is the any direct stress produces a strain in its own direction called as a longitudinal strain, which means we are applying the forces in the longitudinal axis. This length will be changes. Corresponding strain we are calling as the longitudinal strain. Similarly, when we are applying the forces in the length direction, but lateral dimensions, that is the width and thickness, it will be decreased. These kind of the strains we are calling as the lateral strain. So lateral strain is the opposite kind of strain in every direction at right angle to this, which means we are applying the force. So let us consider in this direction. So lateral direction with respect to the right angle to apply the forces, corresponding strains we are calling as the lateral strain. So ratio of this ratio of the lateral strain to the longitudinal strain we are calling as the Poisson ratio, and this is the constant. So when we are applying the forces, the ratio between the longitudinal strain to the lateral strain to the longitudinal strain, it is the constant. That constant proportionality we are calling as the Poisson ratio, the symbol we are using here, mu or maybe the 1 by L. And also the value of the Poisson ratio is the same for the tensile and also compression. Here table is represent the Poisson ratio for the various materials. So these are the very important for the competitive exam point of view. So generally it will be asked so match the Poisson ratio for the corresponding materials. You have to remember, so these 5 materials in general asked for the competitive exams. For the cork material, it is nearly 0, and the concrete it will be vary 0.1 to 0.2, and glass material it will be vary 0.18 to 0.3, and the steel is vary from 0.25 to 0.33, and rubber is 0.45 to 0.5. Now we will discuss about the volumetric strain due to single direct stress. Figure shows the rectangular bar of length L, width B, thickness T subjected to a single direct stress, that is sigma, acting along its longitudinal axis, and this stress will be the tensile in nature. Here we are applying the stress in longitudinal axis, that means in the direction of the length, and here nature of the stress is tensile. So length will be increased, and in lateral dimensions, that is the width and thickness, it will be decreased. So longitudinal strain, let us consider epsilon 1 equal to the increase in length divided by the original length. So also I have to define as the direct stress divided by the Young's modulus. Here nature of stress we are considering the tensile. Now we have to write down the lateral strain, that is the epsilon 2, in the terms of the Poisson ratio. We know the Poisson ratio, that is the mu or 1 by m equal to, it is the ratio of the lateral strain divided by the longitudinal strain. So now lateral strain, that is the epsilon 2, it is equal to the longitudinal strain, that is the epsilon 1 into 1 by m. It is nothing but epsilon 1 divided by the m. So here in the lateral strain, so here dimensions of the width and thickness it will be decreases. So it is the nature is the compressive nature. So we know the epsilon 1 value is nothing but it is a ratio of sigma by E. Same thing here, we have to substitute sigma 1 value, then epsilon 2 will become the sigma divided by m into E. And here I have to consider the rectangular bar. So volume of the rectangular bar will become the V equal to, it is the product of the length, width and thickness. It is nothing but LVT. And I have to consider the delta L, delta B and delta T is the change in corresponding dimensions. Is nothing but change in length, change in width and change in thickness. And the final volume. So delta V equal to the change in the volume. So when we are applying the stresses in the direction of the longitudinal axis, then volume will be changed. Then the final volume it will become the V plus delta V. So initial volume plus change in the volume, that is the V plus delta V. That is we have to write down the V plus delta V equal to, it's a nothing but it will be the product of the length plus change in length into width, initial width plus change in width into thickness, initial thickness plus change in its thickness. So V plus delta V is nothing but equal to the L plus delta L into B plus delta B into T plus delta T. This is also I have to write down the here. Take the L is common, B is common here and T is common. So this product once again I have to write down the LBT into 1 plus delta L by L into 1 plus delta B by B into 1 plus T by delta T. So we know that one this LBT equal to the V. LBT is the volume. Let us consider volume here V, and here. So this is will give the expression. This product it will be give the expression of the 1 plus delta L by L plus delta B by B plus delta T by T plus delta L by L into delta B by B plus delta L by L into delta T by T plus delta B by B into delta T by T plus delta L by L into delta B by B into delta T by T. So here we are neglecting the product of the small quantities. So we are neglecting this all the product. Then final volume, that is the V plus delta V, will become the V into 1 plus delta L by L plus delta B by B plus delta T by T. So here we have to take here, then have to take the, so it will become the V by V, that is the 1 plus delta V by V equal to 1 plus delta L by L plus delta B by B plus delta T by T. So here 1 will get the cancel, then delta V by V equal to, so delta L by L plus delta B by B plus delta T by T. So we know that one thing. So delta V by V is nothing but change in volume divided by the original volume. That is volumetric strain. That is we have to represent the epsilon V equal to the, so delta L by L is nothing but, so strain, so in the direction of the length direction, so that is the longitudinal strain. So let us consider the epsilon 1 plus delta B by B and delta T by T. These are the lateral strains. So nothing but let us consider, so strain in the direction of the width, so that is the epsilon 2, and change in strain, so strain, so in the direction of the thickness, let us consider the lateral strain of the in the direction of the thickness, that is the epsilon T. So delta, so epsilon V equal to epsilon 1 plus epsilon 2 plus epsilon 3. This is nothing but epsilon X plus epsilon Y plus epsilon Z. So here we are applying the stresses in the direction of the length. So length will be increased. So that's why increase in length divided by the original length. That is we are calling as the epsilon 1. This value is sigma by E. Similarly, so strain in the lateral direction, which means in the direction of the width and the thickness direction. So that is the delta B by B, that is the lateral strain. We are considering the epsilon 2. So here decrease in width divided by the original width. So it should be the minus. So we have to representing the, in the terms of the Poisson ratio, it will give the sigma by E into 1 by M. It is nothing but sigma by ME. So nature is compressive. That's why we are giving the minus symbol. So epsilon 2 equal to minus sigma by M into E. Similarly, decrease in thickness divided by the initial thickness, that is the lateral strain in the thickness direction. So this is also here. So decrease in the dimension, that's why we are giving the minus symbol. So this lateral strain we are representing in terms of the Poisson ratio. This value will become the minus of sigma by M into E. So here I have to substitute the epsilon 1, epsilon 2 and epsilon 3 values in the EV value, that is sigma by E minus of sigma by ME minus of sigma by ME. So final volumetric strain, that is the epsilon V equal to, here sigma by E you have to take the constant, here 1 minus 2 by M. So this is the final volumetric strain. for the applying the stresses, that is the single stress in the direction of the longitudinal axis. Same thing here you have to considering the circular bar, then the volume of the circular bar will become the pi by 4 d square into L. So then the volumetric strain, that is nothing but change in volume divided by the initial volume, that is I have to write down the delta L by L plus 2 delta D by D. So here we are applying the stresses in the direction of the length. So this is the longitudinal strain. Let us consider the epsilon 1. So this is nothing but increasing length divided by the original length. So that is the delta L by L, that is the epsilon 1 equal to sigma by E. So let's see in the direction of the diameter point of view, diameter it will be reduced. So decrease in diameter divided by the initial diameter, that is where I am considering the epsilon 2. So minus value it will become. So we have to write down this lateral strain in the terms of the Poisson ratio, that is will become the Poisson ratio into the longitudinal strain. So it's nothing but minus 1 by m into the epsilon 1. So this value will become the minus of sigma by m into E. So final volumetric strain will become the sigma E V equal to delta V divided by V is nothing but delta by E minus of 2 sigma into m by E. So here final volumetric strain will become the sigma by E into 1 minus 2 by m. So thank you.